This video will talk about moving through graphs and connected and disconnected graphs. The least restrictive way to move through a graph is called a walk. A UV walk in a graph is a sequence of vertices starting with U and ending with V such that each consecutive pair of vertices is connected by an edge. So, for example, we could look at a walk Z W S T W P, and this would be a ZP walk. So let's just verify. Okay, we start at Z W S T W P. So yes, each consecutive pair of vertices was connected by an edge, and we started with Z and ended with P. Note that this was obviously not the most efficient ZP walk we could have done. We could have also done a very short ZP walk that would have just been a sequence of two vertices. But that doesn't matter. This longer walk that we just took is also a ZP walk. Something more restrictive is a trail. A trail is a walk in which no edges are repeated. So this is also a trail. This is also a ZP trail. And we can see that it's a ZP trail because no edge is repeated. So we start at Z and then go down to W, then S, then T, then W, then P. And we see that along that trail, no edge was repeated. If we want to further restrict that we cannot repeat vertices, then that's a path. So a path is a walk in which no vertices are repeated, except possibly the first and last. We'll see why that is an exception later. So a walk in which no vertices are repeated. And so we see that this is not a ZP path, and it's not a ZP path because the vertex W is repeated. So because the vertex W is repeated. And just a reminder, the word sequence means that it's in order. So the walk ZWSTWP is different than if we did the walk PWSTWZ. Those would be two different walks. So above we have a sequence of vertices that is a walk and is a trail but is not a path. As another example, we could look at QPSPZ, and that would be an example of a walk that is not a trail. It's not a trail because the edge PS is repeated, and it's also not a path because the vertex P is repeated. And notice that anytime an edge is repeated, a vertex will also be repeated because we go over the vertices on that edge. So any walk that is not a trail is also not a path. Since so far we have no examples of paths, here is an example of a path, QPZW, a sequence of vertices where all consecutive pairs of vertices are adjacent. And notice that because it's a path, it is also a trail, and it is also a walk. Two more definitions here. A circuit is a trail that starts and ends at the same vertex. So remember that a trail is permitted to repeat vertices, but it is not permitted to repeat edges. So for example, the sequence of vertices ZPWSTWZ, that is a circuit. So it did not repeat any edges, although it did repeat the vertex W. However, that would not meet the criteria for being a cycle. A cycle is a path that starts and ends at the same vertex, and a cycle, since it is a path, that means that it cannot repeat any vertices. So this example up here is not a path since W is repeated, and therefore is also not a cycle. An example of a cycle in this graph would be the cycle ZPSTWZ. So that is a cycle. It does repeat the vertex Z at the beginning and the end, but that is allowed, so this is a cycle that begins and ends with Z. And another example of a cycle that begins and ends with Z would be ZPWZ. So these are both cycles. And because they are cycles, because they do not repeat any vertices, they also meet the criteria of not repeating edges. So they are technically also circuits, but we would usually use the more restrictive term cycle when we can. A graph is connected if for any two vertices U and V there is a UV path. So for example, the graph that we've been working with, G, is not connected. And it is not connected because, for example, there is no path between the vertices X and Z. So G is not connected because there is no XZ path, and therefore we would call G a disconnected graph. So G is disconnected. The maximal connected parts of a graph are called components. So this is a maximal connected piece in that there are no more vertices we could add such that it would still be connected. And this is also a maximally connected part of the graph. And so this graph G has two components. A tree is a connected graph with no cycles. So below are two different examples of trees. On the left we've got a tree with 5 vertices, and on the right we've got a tree on 10 vertices, and drawn to look a little more like an actual tree. So given this definition, I'd like you to pause the video for a moment and try to think about, one, how many different, and by different I mean non-isomorphic. So remember that two graphs are isomorphic if you can turn one into the other by just redrawing it. So how many different non-isomorphic trees can you draw on 4 vertices? Is my first question. And my second question is, can you make a conjecture about the number of edges in a tree with n vertices? So I would like you to pause the video for a moment and grab a pencil and a paper and think about your answers to each of these. Okay, so how many different non-isomorphic trees could you draw on 4 vertices? Well, okay, 1, 2, 3, 4. One option is just to make a path through those vertices. So that would be 1 tree on 4 vertices. It happens to also be P sub 4. Another option is that we could say, okay, 1, 2, 3, 4. Now we could start the same way we did before, but now we could say that we want to, instead of connecting in a path, we could connect an edge between those 2 vertices. And now this is definitely a different tree in the sense that these are not isomorphic. These are not isomorphic because this vertex has degree 3, and all vertices in this graph have degree 2. This is a 2 regular graph. So it cannot be that this is representing the same connections between objects. If you believe that you drew another tree that is not isomorphic to either of these, take a closer look, and you should see that if you redraw or rearrange, any other tree on 4 vertices that you draw will be isomorphic to one of these two. Okay, so my second question was for you to make a conjecture about the number of edges in a tree with n vertices. So to start with, you could look at the examples we've had so far. So for example, this has 4 vertices and 3 edges. This graph also has 4 vertices and 3 edges. If we look at the 2 graphs we've drawn previously, this tree on 5 vertices has 4 edges if you count them up, and this tree on 10 vertices has 9 edges if you count them up. So in the examples you drew, you may have observed that there will always be one less edge than there are vertices. So in other words, any tree on n vertices has n minus 1 edges. So any tree on n vertices has exactly n minus 1 edges. That is a useful fact that we will use in the future, so keep it in mind.